Alright, hey, Nick here. I want to do one more video on assembly language, machine language programming for this touch metal board, and we'll see if this is of interest to anybody. If not, I'll probably discontinue this series. But let's dig a little deeper. We've talked about the basic interactions of the board itself, the basic button functions, and so on. We talked about couple of instructions like increment and jump, but let's jump into a programming example and see what that looks like. So let's just kind of the hello world for assembly language programs. Let's just add consecutive integers. Let's just add the numbers 1 through 10 and display the result on the display. We want to think about algorithms. We want to think about, from a higher level perspective, what are we going to have to do to do this series of additions. Eventually we want to get into the ones and zeros and so on of the machine code, and to do that we're going to need to get into the particular instructions, increment, load immediate, and so on. But before we do any of that, usually we want to figure out what's the algorithm. Right? What are the steps we have to have the CPU perform? And then we can take that algorithm, translate it into assembly language, and then assemble that into machine code, and then load the machine code into the memory, and then run it and see what it does. So what's our basic algorithm? I mean, for you and I, we would just go to a calculator and do 1 plus 2 plus 3 all the way up to 10. It's a little more complex for a simple 8-bit processor. We need something like a running sum. So I'll start off with some sum, which is equal to 0. And we need to know which number we're about to add. So I'm going to say, let's start with the number 1. And now I'm going to do a loop, right? We talked about jump instructions last time. So what am I going to do? I'm going to do sum equals sum plus our number. So the first thing we'll do is we'll add 1 to our running sum, which just gives us 1, of course. And then we need to move to the next number. Number equals number plus 1. And then we want to go back and do this again. But we don't want to do it forever. We want to stop after we've added the number 10. So the way I've written this, after I add the number 10, I'm going to increment num to be 1. And so I'm going to say if num is not equal to 11, then let's go back to the top and do it again. And then we can say, output our running sum and halt. So that's like a high-level language program, right? We don't have instructions for sum equals sum plus num, but this is a high-level view of things that we can each translate, translate each of these into a set of one or more assembly language instructions, right? So this is what we begin with. And at this point, I'm going to modify this a little bit, because checking to see if a number is different from 11, yeah, we can do that, but we could make it a little simpler, because comparing to 0 is always easy in assembly language. Comparing to something other than 0, a little more complex. So let me rewrite this in a slightly different way. I'm again going to start with my sum equals 0, but I'm going to initialize the number I'm adding to 10. And now I'm going to make a loop, sum equals sum plus our number. And then I'm going to say num equals num minus 1. So I'm going to actually be doing 10 plus 9 plus 8 all the way down to plus 1. Okay, why is this better than adding up from 1 to 10? Because the last number I want to add is a 1. And after I do sum equals sum plus 1, this will change num equal to 0. So now my branch condition says if num is not equal to 0, go back up to the top. And that's an easier condition to test for, right? I'm kind of pre-using my knowledge of my assembly language instruction. I know I have a jump if not 0. And I can just put in the address of num, and if it's not 0, it'll go ahead and take the jump. Whereas to do this, I would need to take my number, I would need to subtract 11, and then say if the result is not 0, go ahead and jump back up. So here's the program I'm going to actually code into assembly language. And let me move this over onto the side here. And let's see what this looks like. So I'm going to store my sum and my number somewhere in memory. Doesn't matter where. I can pick for myself what location I want to store these at. So remember, we like to think about registers when we're working with this processor. So my sum, I'm just going to store that in R0, and my number, I'm just going to store that in R1. So rather than storing it at a location in memory, I'm going to use my special purpose registers to hold the value of sum and num. Alright, so how do I set my sum equal to 0? I need to find a way to put a 0 into something. Well, I have a clear instruction, CLR, and I can put in a register after that. So I'm just going to say clear register R0. And then I want to put the number 10 decimal into R1. Well, I have a load immediate instruction which says load this value into whatever register I specify. So I can say load immediate R1, comma, and I'm going to do 10 with a period at the end to indicate this is 10 decimal as opposed to 10 in hex or in octal or in binary. Alright, now I'm going to want to come back repeatedly to this next instruction. So I'm going to put a label here so I can refer to it. And now I want to do sum equals sum plus num. In other words, I want to set R0 equal to R0 plus R1. Well, I have an add instruction that adds 2 registers, and it stores the sum in the second register. So if I just say add R1 comma R0, what is this saying? This is saying R1 plus R0 gets stored into R0. And remember, R1 is our num, so this is saying num plus sum gets stored into sum. Right? That's exactly what we're trying to do. So this add R1, R0 will work. And then num equals num minus 1, that's a decrement instruction. Decrement subtracts 1 from a register. So I can say decrement, and which register? Num, that's R1. Alright, now the branch is a conditional branch, right? So I have to note that when I decrement R1, when I do any decrement, the flags that are updated are the carry, the negative, and the 0 flags. That 0 flag is the one I'm interested in. So every time that I do this decrement instruction, this Z bit of the status register gets touched. And if the result is not 0, Z will be clear. But if the result of this decrement is 0, in other words, if num is equal to 0, Z will be set to tell me, hey, whatever you did last resulted in a 0. So if I want to jump if num is not 0, I want to jump if R1 is not 0, I can just say jump if not 0. So this JNZ instruction is going to work. Jump if not 0. Back to loop. And then otherwise I'm just going to say halt. Alright, there's my assembly language program. Next thing I need to do is translate this into machine language. So let me come over here just restrict down to my assembly language program. And let's write a nice, clean, assembled version of this program. So I'm going to have an address. I'm going to have contents. And I'm going to have assembly language. And I'm going to begin at address 0. And my first instruction is going to be clear R0. Alright, so how do I code a clear R0 into machine code? So clear register, the coding is 1, 2 followed by the register number. So this is stored as a 1, 2 followed by a 0. Okay, that's a single byte, a single 8-bit instruction. So my next address is 1, and that's where I'm going to say load immediate R1, 10. Alright, how do I code load immediate? That takes 2 bytes. The first byte is 07 followed by the register number. So that's going to be 07 followed by 1 because we're loading into R1. And then the next value is the 8-bit value of the number we're loading. We're loading in the number 10 in decimal, so in octal that's a 12. Right? If you don't want to do the conversion, you can look up a 10 down here. It's an I test here, and that's a 1 followed by a 2. So 12 octal is 10 decimal. Okay, so this was at location 1, 2. The next instruction is going to be at location 3. And that's going to be where our loop begins. So I'm going to put a label here, loop. And then I'm going to, there's no code associated with the loop, so I'm just going to stay at address 3 in our memory, and I'm going to say let's add R1, R0. Okay, the add instruction, it's another 2-byter. The first byte is 020, that's the opcode. And then the next byte has 3 pieces to it. There's a bit called M, which says what mode are we using to address our registers. And then there's the source register and the destination register. Okay, we're saying add R1, R0. We're just going from a source to a destination, as opposed to using indirect references on the source or the destination or both. So our M is just going to be a 0. And then our source register is a 1, and our destination is a 0. So add R1, R0, we put a 1 and a 0 for the S and the D. So the way that these instructions are coded in octal works fairly painlessly, right? We don't need to do a lot of bit level manipulation. We can kind of stick with octal digits. So add source destination, just source register, destination register. Alright, that's going to be stored in memory locations 3 and 4, so our next word is at location 5. That's our decrement R1. And our decrement instruction is a single byte. It's a 1-1 followed by the register number. So this is 1-1 followed by a 1. Next instruction goes at location 6. That's our JNZ, our jump if not 0 loop. Alright, jump if not 0, it's going to take 2 words. It's a 006, that's the opcode, followed by AAA, that's the address to which we want to jump. What address are we jumping to? We're jumping to loop. Loop was at address 003, so that's the jump if not 0 loop. And then, oh, I forgot to display the result. So let's do an output, and output our sum, which is R0. So that'll display our answer on the output register, and then we can halt. Alright, so this was at location 6, 7, so here's the next location, which is 10 in octal, that's 8 in decimal, and we want to say out R0. So our output instruction is also a single byte, so it's a 17 followed by the register number. So to output R0, that's just 170. And then our next location is going to be 011, and that's where we're just going to say halt, and a halt is just opcode 002. So there's our machine language instruction. It's these sequence of bytes. We store them in memory and run it, and we should have our executable program. Alright, so let's go ahead and put this in. I've just powered up my machine, but if you're in doubt, you can hit reset twice, and a 1 that clears out the entire memory, resets all the registers, and so on. So let's just start storing these numbers. So I'm going to do a 120, and I'm going to hit the deposit button, and then I'll just keep typing these in. So 071 deposit, 012 deposit, 020, and so on. 010, 111. And you can spot check yourself along the way. I've got a 006 here. That means it's expecting me to deposit location 6. Well, that's where I am. So 006 deposit, 003 deposit, 170 deposit, and 002. Alright, so I just deposited into location 11, so it's up to location 12. So I didn't miss anything. Let's go back and look at our program and see if we've done the correct thing. So let me go back to our assembly language program, and I forgot to write down the halt here. We'll just add that in. And I'm going to say 000, and I'm going to hit examine. And I'm going to change my display mode to make it a little easier. I can see my clear R0 right here, but I'm going to change it to this display where I just see the instruction and the address. So I've got a clear R0, and each time I hit examine, it should show me the next instruction. So there's my load immediate R1, 12. It's 12 octal, 10 decimal. I'm not going to see anything for loop, but I'll note that loop is at location 3. There's add R1, R0. And this is a 2-byte instruction, so location 4, that's not one of our instructions, that's in the middle of this add. Here's the decrement R1. Here's the jump if not 0 back to location 3. That's part of the jump. Here's the output to R0, and then here's the halt instruction. Alright, so I'm going to go ahead and put my display back to where it normally is. I'm going to say reset, which puts my my PC at 0, and I'm just going to go ahead and run this. And it will run, it'll loop 10 times, and when it's done, I can see my output is a 67, and if I change my display mode, I can see it bigger here. Output is 67. Alright, that's 67 octal. So what is 67 octal? So 67 base 8, that's 6 times 8 plus 7. 7 times 1. That's 48 plus 7. That's 55. Well, if you add up the numbers 1 through 10, that's what you should get, is 55. So this is correctly adding up our numbers from 1 to 10. So that's cool. That's an example of a complete kind of development process from the algorithm to the assembly language, to the machine language, to the toggling it in, and then ultimately testing it. And it's not as cumbersome as you might think once you get used to it. For example, it might be useful to look at the running sum as we go ahead and calculate it. So maybe after I do this add R1 to R0, I want to go ahead and output my running sum. So I could stick my output instruction right here. Let's say output R0. And I already know that's going to be a 170. Well, it's going to change my addresses, right? It's not going to change this 03, but this is going to be 170. This will be location 6. This will be location 7 and 10. And then I'm not going to need this output here, and 11 will be the halt. So I have to make some changes to my assembly language program, but I don't have to type the entire thing back in. My first change was location 5, so I can say 005 examine, and it was a 111. What I want it to be is a 170, so I'll do a 170 deposit, and then a 111 deposit, and then a 006 and a 003, and then my halt instruction is still there. So let me reset this, and let's just look at the output register, and let's go ahead and run this, and we should see the output register update as it does its sum. Now remember, we're counting from 10 to 1, so it's going to start off with 10 and then 19 and so on, and it's going to be an octal, but we should see the output increase on its way up to the final value of 67 octal. So let's go ahead and run that, and you can see it's counting up 10 steps, and it eventually gets to 67. So again, you know, key steps: algorithm, and then machine language, and then assembly language, and then load it into the memory, and then run it, and if it works, great. If not, start debugging. If something was wrong, I could go back and I could start stepping through one instruction at a time. And if my output value is not right, I could say, well, let's take a look at location 400. That's R0. That's a 33. Let's look at location 401. That's register 1. That's a 7. And maybe I could say, oh, you know, there's my problem. It's supposed to be something else, right? So anyway, that's an example of kind of a start to finish development process for assembly language, machine language in general, and the touch metal board in particular. All right, let me know if you like this. I can continue and go deeper into more complex programs in a future video. Thanks, take care, bye.